Okay, welcome to Unit 6. So this is the last unit for the course and potentially one of the more practical units, solving differential equations using numerical methods. Okay, so we're going to have an introduction to that today. And we're going to focus on first order ODEs, and we're going to firstly focus on a method called Euler's method. Okay, so the vast majority of differential equations, in fact, do not have a solution that's able to be written algebraically, either explicitly or implicitly. So for some of the ODEs in Units 1 and 2, you'll recall that we drew this thing called a direction field. So the direction field was some visual way of trying to understand what the behavior of this differential equation was doing. Okay, an alternative way, if we actually want to have quantitative numbers, we can use numerical methods to approximate the solution of differential equations. Okay, so we do need an initial condition. So really, when I say numerical methods for differential equations, really what I'm talking about in the context of this class is initial value problems. Okay, so we'll start with this basic initial value problem. So dy by dx equals some function of x and y. So we could be some linear or nonlinear function here, f. And we have an initial condition when x is equal to x naught, y is equal to y naught. Okay, and what we want to do is approximate the solution to this initial value problem by discretizing the x-axis, okay? So the independent variable, we're going to discretize. So when we solve a differential equation algebraically, when we get a solution, for example, in terms of exponential functions, we have a solution that's continuous. So any value of x we have a solution for. But when we use numerical method, we only have solutions at discrete values of x. Okay, so we divide the x domain up into, in our case, equally spaced points. So in the image here, x0, x1, and x2. So at each of these points, we're going to try and find the solution to this different initial value problem. At the points in between, so halfway between, say, x0 and x1, we do not have any information about the solution using these numerical methods. Okay, so we only get solution or values of the solution, values of y at these discrete points, x0, x1, x2. Okay, and the distance between each of these points, in this class, we're just going to call that the step size h. And in this class, we're just going to take that step size to be constant. Okay, there are other numerical methods or theories where we can actually change that step size to get a better accuracy and a better computational efficiency. But in our case, we're just going to keep that constant. Okay, so each of these points can be represented by this equation here. Xn, so the nth point along the x-axis, is equal to x0, so our initial condition, our initial point, plus n times that step size h. So n here starts at 0, so when n is 0, we get the initial condition, x0, and n is an integer. Okay, so 0, 1, 2, 3, 4, 5, and so on. So just to summarize, we're going to start here at this point. We're going to give the initial condition y is equal to y naught when x is equal to x naught, and we're going to apply some numerical method to get the solution at this point x1, and then again to get the solution to this point x2. Okay, so what we can do to derive this numerical method is we can integrate the ODE on this interval xn to xn plus 1. So n could be any of these 0, 1, 2, 3, so on. So this is just a general formula. Okay, so our ODE was this: y prime dy by dx equals some function of x and y. And I'm just going to integrate both sides of that equation between xn and xn plus 1. Okay, so I'm taking the definite integral between in these gaps. So the two points here, x1 and x2, I'm taking the integral along that segment of that line. Okay, you can see here the integration variable is t. Well, this is just a dummy variable for x, because when we use the definite integral, that t is going to be replaced by xn and xn plus 1. Okay, and if I do that, well, the left-hand side, if I integrate dy by dt really now, and I evaluate it at 2 points, I actually just get y at xn plus 1 minus y of xn. So I've taken that y of xn to the right-hand side, plus whatever this integral is. We don't know what this function f is. So of course whatever that function f is depends on the value of that integral. Okay. So what this is saying is that to get the updated value of y at the point xn plus 1, we just take the value of y that we already know, so the value of y at xn, plus this integral, okay? And so this equation gives us a way to approximate the value of y at the next spatial position. So we know the value of y here at x0. We apply this formula to find the value of y at x1, so we move to x1. And then we do the same thing. We know the value of y at x1 over here, and we apply this formula to get the value of y at x2. Okay. The last piece of the puzzle, or the last piece of the method, is to figure out how to evaluate this integral here, or let's say how to approximate that integral here. Okay. So Euler's method basically is saying that this integral can be approximated using a linearization. Okay, and what do I mean by that? Well, if I plot this function here, if I plot the function f of t here, and I'm trying to evaluate this integral, the integral from xn to xn plus 1, which has gap h, size h, basically what this integral is the area underneath this curve here. The red curve is f of x, y, so the function f. The integral of that function is the area underneath that curve. You remember this from first year calculus, right? Or even high school calculus. Okay, what I'm going to do then is say, okay, well, at this point here, xn, my function is equal to xn, yn. And let's say we know the value of xn here, and we know the value of yn. What I can do is I can just draw a horizontal line at this point here and say, okay, well, if I draw a horizontal line of length h, then I can sort of approximate the area under this curve here by basically multiplying h by the height of this function. So the function f evaluated at xn, yn. Okay, so this yellow area here is the approximated area under this curve, or let's say the approximation to this integral, okay, in the Euler's method, or in the numerical method. The bit in blue that is left over is the error, okay? So I've approximated this integral using some very simple guess. There's some error associated with that guess, and that error is going to be smaller as I take h to be smaller, okay? So if this gap wasn't so big, then this error in error in the area calculation would be less. So basically what we're saying is that this integral, this area under the curve of the function f between xn and xn plus 1 is equal to h, the width here, multiplied by the function evaluated at xn, yn. So we get this rectangle, the area of a rectangle is length times height, right? So we get this approximation for the area. So therefore, Euler's method basically says, if we know xn and we know yn, then the updated value of y at n plus 1 is equal to the value of y at the point n plus h, the step size, times the function evaluated at xn, yn, which we know. Okay, we will know that. So n is 0, 1, 2, 3, 4, and so on. And y0 is the initial condition. Okay. So this is called Euler's method. This is called an explicit method. And you might notice that we can actually write this equation for Euler's method here actually represents a straight line. Okay, so we generally think of a straight line as y equals mx plus c. So here y is just yn plus 1. The plus c is just plus some constant. So this yn is a number that we know, some constant. The gradient m, or the slope, is equal to the function. So the function here represents the slope of the line. And the x discretization, or the x variable, is h here, right? So we choose h to be some discretization. So basically what this is pointing out is that the Euler method moves us in a straight line with the slope f of x in the function evaluated at x in yn. Okay, and just a bit of terminology. When we write on the left-hand side here yn plus 1, so that could be y0, y1, y2. The point is, when we write it with a subscript, y with a subscript, we're talking about the approximation here, or the numerical approximation of after n steps, or n plus 1 steps. Y in brackets xn plus 1, so x sub n plus 1, is the exact value of y at the point xn plus 1. So this is like the exact solution. So when we see y and then something in brackets, it's the exact solution to the ODE, which we may or may not know. When we see y with the subscript, y subscript some integer, that is the approximation using some numerical method. Okay. The difference between these two, of course, is just the error in the approximation. So if we have some solution curve here, this curvy thing here, at this point x0, so our initial condition x0, y0, at this point here, we evaluate the slope by calculating the function f at x0, y0. We extrapolate along that, or we move along that line of slope f of x0, y0, and we get to this point here, which we approximate as x1, y1, okay? But the true value of the ODE at that point is x1, y evaluated at x1. So the difference between these 2 points here is the error. So we start here, we move along that straight line of slope f of x0, y0 until we get to x1. Okay, and we get some value, some approximation y1, but the exact value is y at x1. And the difference between these two is the error. Okay, so this should become a lot clearer looking at an example. So we have the very simple ODE dy by dx equals y, which of course we know has some exponential solution. Let's just say that we didn't know that, we didn't know the solution. We might like to approximate this using Euler's method, okay? With step size h equals 0.1. It turns out that, of course, you know how to solve the separable equation. So the exact solution is y is equal to e to the x. So this can be useful to just check the accuracy of our numerical method. We're given x0 equals 0. And when x0 equals 0, y0 equals 1. So this is our initial condition here. So what we're going to do is we're going to track the values of, well, xn is just a constant, right? It starts at 0 and we're moving up in step size of 0.1. And yn is going to be our approximated value. Okay, well, I have some terms in the table here: absolute error and percentage relative error. We'll come back to these error definitions later, so we'll just worry about the first three columns here. Actual value is just the value of y at xn. Okay, basically it's the exact solution. So we can compare this column yn, the approximation, with the exact solution just to see how accurate we're getting. Okay, so we're going to solve this now by using Euler's method. So, okay, well, y1, so when n equals 0, y1 is equal to y0, our initial condition, plus h, the step size, which is 0.1, multiplied by f, the function evaluated at x naught, y naught. What is the function in this case? Well, dy by dx equals f. So f here is just y. Okay. So yeah, just to point out, y naught equals the initial condition, y naught equals 1. H is the step size, and f is just the right-hand side of the differential equation. Okay, so what does this equal? Well, if I rewrite this out, I get y naught plus h times y naught, okay? So the right-hand side of the ODE is just equal to y, and I'm evaluating that right-hand side at the point x naught, y naught. Okay, so y evaluated at y naught is just y naught. Okay, and in our case, y naught is 1, h is 0.1, so we end up with y naught 1 plus h, so plus 0.1 times 1, which equals 1.1, of course. So we'll fill in our table here when x is equal to 0.1, so we've taken a step size of 0.1, our approximate value of y is 1.1. Okay, and if you put x is equal to 0.1 in this exponential, so the exact solution here, e to the 0.1 is 1.1052. So you can see here that there is a small discrepancy between the approximated value 1.1 and the real value of 1.1052. Okay, well, we can do this again. We can say, well, y2, so y at x equals 0.2 is equal to y1, the previous step, so y1 here, plus h times the function evaluated at y1. So the function is just y, so we just get h times y1. Okay, so y1 we found was 1.1. And if we put that in the Euler's equation, we get 1.1 plus h, so 0.1 times y1, it's 1.1. If I put that in my calculator, I get 1.21. So n equals 2 here, xn equals 0.2, so we've taken 2 steps of size h equals 0.1. Yn is approximated as 1.21. And if I put the actual value into the exponential, the exact solution, so the exponential of 0.2 is 1.2214. So again, a little bit of error there. We can continue this on. y3 is equal to y2 plus h times the function evaluated at y2, 1.331. And we can continue on like this until we get to whatever point that we want to get to. So let's just assume we want to take 10 steps here so that we can get to x equals 1. Okay, so after 10 steps, our approximation is when x equals 1, y is equal to 2.5937. The exact value at x equals 1 is e to the 1, which is 2.7183. So there's some small error there. So y10, so y after 10 steps, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. y10 is equal to 2.5937. Y at x equals 1, which we usually just write as y1, is equal to is actually equal to 2.7183. So y10 is 2.5937. Y at x equals 1 is 2.7183. So the error is the difference between them. Okay. So yeah, the approximation here, the exact value. Okay. So we get pretty close, and again, if we took a smaller step size h, then we would get even closer. Just quickly talking about these error terms here. The absolute error, this first column in here, is the actual value, so the exact value minus the approximate value that we've approximated using the numerical method. Okay, so the actual value here in green, this exact solution basically, the approximate value is our numerical method value. Well, in this first line here, this is basically just going to be the actual value is 1.1052 minus the approximated value, 1.1. We take the absolute value of that, so it's always positive. So if we do that calculation, the absolute error is 0.0052. And then we can do that for every step here. So for example, in this last line here, when x equals 1, 2.7183 minus 2.5937 equals 0.1245. Okay, so this is the absolute error between our actual exact solution and our approximated numerical solution. So note that the error grows the more steps that we take, and that's basically because, well, after we make the approximation of one step, so from 0 to 0.1, that approximation already has a little bit of error in it, okay? So then when we make the next step, we're basically making a little bit more error, but we're starting from a place that already had error, so we're sort of compounding the error there. And then as we take more and more steps, we compound more and more error together. Okay. The second column here, this relative error, that is just the absolute error. So what we just calculated there, actual value minus the approximate value, divided by the absolute value of the actual value. So it's basically actual value minus approximate value divided by actual value. And of course, to turn that into a percentage, we would just multiply that by 100%. So we have the absolute error, so this column that we just calculated here, divided by the actual value, multiplied by 100%. So the absolute error is 0.0052, divided by the actual value, 1.1052, multiplied by 100%, is 0.47%. Okay, and as we go on here, we can calculate that for every step we took in the numerical method. And what we find is at the end, the approximate value that we had has a percentage relative error of 4.5% or so. Okay. So just to point out, we used the step size of h equals 0.1 here, so we took 10 steps to get to x equals 1. If I decided to do the same thing, solve this ODE or this initial value problem using Euler's method, but instead of taking a step size of 0.1, I halved the step size. Okay, so if I took h equals 0.05, I have to take 20 steps to get to the same x equals 1 location. Well, because the step size is halved, I have to take double the number of steps, so 20 steps. But actually, that reduces my percentage relative error from 4.58% to 2.39%. So reducing the step size h leads to more work. I have to do double the amount of work, right? Because I'm going from 10 steps to 20 steps. But actually, it looks like it's approximately halved the error. Okay, and we're going to talk about that that more in tomorrow's class. The approximation of the error based on our value of h. Okay, I'll see you in tomorrow's class.